Okay, guys, welcome back to section 2.3, isotopes and average atomic weight. Today, we are going to be looking at isotopes. And to begin with, let's define what that means. These are atoms with identical atomic numbers, but different mass numbers, okay? Therefore, what this translates into is the same number of protons, because we've got the same atomic number, but different mass numbers. Therefore, that means what we've got here is if the mass number, remember, is equal to number of protons plus number of neutrons, that means there's got to be a different number of neutrons in that nucleus. So because, therefore, of the different number of subatomic particles in that nucleus, like we just said, is the different number of neutrons. So the result of this is we have different isotopes, and those different isotopes have the same chemical properties, but a different mass. And the different mass arises, again, remember, from the different number of neutrons found in that nucleus. These different isotopes, therefore, have different stability because not all isotopes are equally stable. However, different isotopes have different naturally occurring abundance on the face of the planet. This affects the mass of any sample of an element due to the variance in the mass within the sample of that element. What that means is we have natural abundance that is varying for each element. Okay, we must calculate an average mass of the element based on the natural isotopic abundance, because what we must do is actually find the average mass rather than the mass of a specific isotope. A warning is that this average is what we call a weighted average. It's an average that does not equally draw from the values being averaged. It is not 3 plus 4 plus 5 divided by 3. That would imply that the abundance of 3, the abundance of 4, and abundance of 5 are equally contributing to that final average value. Let's do an example, okay? That's the best way to actually understand this. Here's an example. An element has the following natural abundances. An abundance of 90% with this mass, 0.26 abundance with that mass, and 8.82 abundance with this third mass. You calculate this utilizing the following method. So first of all, anytime you use a percentage, you have to convert it to a decimal. 0.9092 multiplied by the aforementioned mass, 19.99 AMU. And then we're adding to that the second abundance converted to a decimal, quite small, 26 times 20.99 AMU. And finally add to that the third abundance converted to a decimal, 82 multiplied by the mass, 21.99 AMU. Plug that into your calculator and you'll find that the value is 20.169 AMU. Now remember, we want to apply significant figures. Looking at these values, you can see that the abundances are down to 2. So theoretically, if we were asked to do this with the correct number of sig figs, we'd probably have something on the order of 21 AMU. Okay, but for further calculation, you would want to stick to utilizing this value here. All right, thank you. And we'll talk about this in more detail in another example.